there's a question about the spring.
Yeah.
I know in class that we did that, and that all we had to do was take the integral of the function, and it came out to be kx. It used to be, it was...
In class we did only specific interval, and I don't remember what exactly your problem asked for. The situation is the same, but in class we did from the equilibrium to, I don't know, 1 unit to the right.
Mm-hmm.
Yeah.
Okay. I just had a quick, is the k supposed to be negative? Because the example in class, it was negative.
No, I actually had negative, and then I added negative sign there, because, so it's negative k with k positive. Okay. Which makes more sense, because k is supposed to be a characteristic of the spring, which, so it's the stiffer, the larger, or something like that. So I think it is a better idea to think of k as positive, but with a negative sign in front of it, when in the equation. Yeah, so you got to make sure that matches. Okay. Okay, so the limit. So something that you saw in Calculus 1, and that's why we're gonna not spend as much time as otherwise would be appropriate. But I'll try to take use as much as possible what you experienced in Calculus 1, and then concentrate on things that are actually different. So this looks familiar, and it is pretty much the definition of a horizontal asymptote, except you had something like this: f of x minus L less than epsilon, okay, which is almost simply different notation for the same thing, okay. But remember once again that picture that we had, dots are replaced or with a curve behind it. So that's how you produce a sequence from a function, okay? And so we're going to do that in a minute. So just to remind you what this means, it means that on your graph, this is ends follow the x-axis, so I could have both x and n here. Then y is still the outputs, on the vertical axis. This line is y equal L. And then what we're talking about is we are progressing as far as necessary to our right. I missed the n larger than n capital over here. Okay, progress as far as necessary to our right in order to make sure that to ensure what that our graph of either the whole graph of f or the graph of the sequence lies within a band of values. So this is y equal L plus epsilon, and this one is y equal L minus epsilon. So my graph of the function, or my just the graph of my sequence, have to remain within this band. Okay, so it might start wildly like this, but then as it reaches n, it's supposed to stay within it. Okay, like this. So that's what the requirement is. It is supposed to happen no matter how small epsilon we choose. So we make the band narrow and narrow, and we still can find that number n that is required by the condition. To illustrate this, I have a picture. Okay, so if we look at this one, 4 pictures consecutive, one at a time. So if I look at the first picture, then what is it? My L is here. This is where my L is. Okay, and then this is L plus epsilon, this is L minus epsilon, okay? And all I have to do is to ensure that my sequence, this is my sequence, fits within that band, okay? And indeed, if I choose this n over here, it does. So these do not, so that's why I have to move n to the right, okay? So that's the first stage. Then I keep making epsilon smaller, so that's the next stage is this, L minus epsilon, L plus epsilon, and this is still L. Okay, and then as you can see, some of those do not fit anymore. So for example, this one used to fit into the previous band, and now the band is too narrow, so that's why I have to move. The goalpost has been moved, and therefore our n has to also move, and as you can see, I have to progress n to the next one. Okay, so the epsilon narrow, the n is larger. Okay, and then that repeated several times. So once again, my epsilon has become even smaller, my band has become even narrower, and therefore, so that's the smaller n, the larger n has to be. And furthermore, so it happens the total of 4 times, as you can see, and you can see how n progresses from left to right, forced by what? By the fact that the epsilon is small, and some of the values of the sequence do not fit anymore. Okay, so as I said, if I try to take this this band to the left, then some of, well, maybe not this one, but definitely this one falls out, and so that's why I cannot keep the n the same as it was in the previous picture and have to move it more and more to the right. So that's the idea of the limit, which mimics the idea of the limit in calculus 1. The difference is almost negligible, except we can be more, it is more convenient for us to illustrate this with not just pictures but also with numbers. So for example, if we look at this, we have a sequence of numbers. Okay, so AN is first column, the AN the second column. We can see the illustration here. We see that the limit must be 0. So let's try to implement the definition. So once again, this is the definition with that function. So for every epsilon, no matter what we pick, we're supposed to find n so that the tail of the sequence starting with n capital fits within that band. Okay, so what does it mean numerically? Let's try to carry out a few times. So I'll put epsilon here, and I will put n here. Okay, so let's start epsilon a small number, say a very large number, say 0.3. Okay, so 0.3, I have to find a place on my sequence after which all the values of my sequence will be within 0.3 from 0. Okay, can you see that n? These are the values, and you can see the distance to 0 is the value itself. So in other words, we're looking for the values here that will be from that point on between negative 0.3 and 0.3. So what's the value of n? Look at it. Very small. It becomes small very quickly. Here's the value.
3.
That's right, 3. So starting with 4, everything is less than 0.3. So n is equal to 3. Okay. If I go with 0.1, this is where it starts, right? From that point on, everything is between negative 0.1 and 0.1, if at least by examination. So the value of n is then 7. Everything from 7 on. I could put here a larger number. That would not be a mistake, as long as you can indicate where, at what point things are surely at the right place. Yes?
Would that be 9 instead of 7?
0.1, so it's definitely not 7. 8 is fine. 8 is the smallest one. So starting with 9, it all depends on wherever I'm using the inequality here. Is it strict inequality or non-strict? Usually it is. How about let's make it non-strict inequality, so there will be no doubt. So starting with that point, inclusive, the numbers have to fit into our band. So for this one, it will be 4 then, or 5 or 6. They're all good. And here with 0.1, I have to start with 9 indeed. Okay. 0.01. 0.01. Scrolling. As you can see, all of these are bad numbers. They do not fit. So where does it start to fit for the first time? Well, I'm still looking for it. I'm not sure I have enough data. Okay. I think this finally is starting to be consistently below. No, it's still not. Still no. Okay, no. So still 0.1 keeps repeating. Okay, so n has to grow large and large for us to make sure. But seemingly this is it. You would have to actually do some algebra to confirm that our choice over here would be okay, right? This is 97 is okay. You agree? 97 is okay, but you can see that it is certainly quite a step. So if I try 0.05, then we're definitely out of numbers. 0.05. No. So let's give it a few. Okay, but it does seem that I think we have reached it. It's here somewhere. 0.0. I meant, what did I put it? 0.005. Did I meant 0.005. Okay, so closer to the end of this, we are there. Okay, closer to the end. So if you have to, like I said, you don't have to indicate exact value for n, the smallest possible value. So how about I put 284 just as well? 284 seems to be working. Okay, so just as well. 284. Okay, and so as you can see, we have this worked out just fine. Okay, so that's how the definition works. The challenge of the definition is that we have infinitely many steps, and therefore for every epsilon, not only these, doesn't matter how small you go, you have to go even smaller in order to confirm that that indeed the limit is not just approximately equal to 0, it is equal to 0, and it does not. It continue to accumulate towards 0 and not continue to oscillate. This picture is in fact not entirely convincing. If you see, you can see the amplitude, the swing seems to diminish, but does not diminish fast enough for us to say, well, it definitely diminishes, definitely disappears. It never disappears entirely. So it is a challenge of calculus dealing with infinitely small quantities. And to get to infinitely small quantities, you might have to make infinitely many steps. Okay, so that's the challenge. That's why the definition looks the way it does. So for every number L, for every epsilon rather, no matter how small, no matter how many zeros you have, you should find that n capital. So if you remember doing that in calculus 1, it means that you have to actually have a formula. You have to have a formula, and as it depends, n capital as it depends on epsilon. Okay, if you can have it, then you can actually prove it by algebra that that's why it works out. In general, maybe not. So just to refresh your memory, maybe how about 1 over n minus 0 less than epsilon for n larger than n. You can figure out now n capital in terms of epsilon. How? 1 over n should be less than epsilon, so pick n capital equal to what? So how do I make sure that 1 over n is less than epsilon? What should I pick n to be? I could express it in terms of epsilon. It's the same as to say that, what is it, n larger than 1 over epsilon. So that's roughly what you can just pick 1 over epsilon. Okay, and it works out. When the formula is simple enough, it frequently works out as simple as that, and you might have done that in calculus 1. So usually that's if you want an integer, that's what you do. You put that bracket here. Remember what the bracket stands for? Least integer value, or largest integer value that is less than that number. Okay, so if we need an integer. Okay, to demonstrate this one more time, specifically how it is different from functions. Remember how we created this function. Look at it. It is actually sine n divided by n. That's what it is. Okay. But let's. So in other words, it comes from a function. This is our function. The green one is the actual function. So I could do better than that and have a function specifically that is not have a specific sequence that does not come from a function, and that is accomplished by replacing sign with something else that oscillates. A sequence that oscillates without involving any trigonometry. It's very simple. Negative 1 to the power of n oscillates. So when n is even, so you multiply negative time by itself n times, so it's going to be 1, and n is odd, you have negative 1. So in other words, this sequence oscillates between negative 1 and 1 infinitely many times, doing anything, nothing else. Okay, so once again, an oscillating sequence, literally looking like this, that does not involve any trigonometry. Okay, so first of all, the question becomes, I hope, what's the limit of the sequence, of the new sequence? So remember what you are facing is that you're supposed to have a number. You're supposed to have a number. So this is our sequence. But what we expect to have is some kind of number L, okay? And we're supposed to be able to fit our sequence in a band around that number. And that band can be as narrow as we like. So what's the limit? There's no limit. There is no limit. There is no way we can fit. If I pick epsilon equal to, say, 1/2, there is no way we're going to fit our sequence in a band of width which is only 1. It oscillates between negative 1 and 1, so the swing is 2. So it's not going to fit into a band that is any smaller than that. So there's no limit, and the words that we use, just like in calculus 1, is the sequence diverges. Otherwise, it's called we say it's converges. Okay, so for example, 1 over n converges to 0, but negative 1 to the n diverges. Okay, so there are less exotic examples of divergent sequences, such as, for example, n is equal to n, also diverges. Okay, just going straight up. Okay, so we can be more specific here. Limit of n goes to infinity is what? The limit of n as n goes to infinity is infinity. Yes. So in other words, divergent has two scales, two categories: divergent plane and divergent to infinity. Okay, so divergent to infinity is not as bad because at least we can say something positive or informative about that sequence. Even though there is no limit in the sense of a number, it still has something something of a pattern. So oscillation between negative 1 and 1, that is not a pattern. There's no accumulation of any kind. But if you were approaching infinity, that is something. Okay, so in a sense, you can say that the limit, infinity is the limit. Okay, even though it's not a number. Okay, so let's go and do this thing one more time, and I want to replace, in this example of a sequence, I will replace n, sine n, with negative 1 to the n. Okay, negative 1 to the n. I'll put here negative 1 to the n. I think it's supposed to work like this. You just need so in other words, I start with my sequence 1 over n, which we just saw, negative 1 to the n, which oscillates, but then I still divide it by n, okay? So that way, we're going to have things slightly, so then there will be still some kind of convergence. Okay, I'll go all the way. There should be a lot of difference. As you can see, it doesn't differ that much. So here's the sequence. So as you can see, the green one is really non-informative, so I'm gonna drop it. I'm gonna drop the green function because it's just a connects the dots. There's no function behind the sequence, right? So there is negative 1 to the n. There is no trig function behind it. It is just a sequence, a pure sequence. That's why I want to change this chart type and remove the function from it. Scatter plot. This one. Okay, so as you can see, there is no function behind it. That's how it behaves. It oscillates entirely in a very strict way, unlike the previous example when it sometimes is positive, positive, negative, negative, positive, negative. This one goes straight positive, negative every time because that's what negative 1 to the n does. But then as you can see, the pattern is the same. These numbers might not work anymore, so you'd have to go through these numbers again in order to confirm, at least with numerical evidence, that there is a convergence here. But the technique is the same. Okay, so let's do a couple of examples. Well, here's another example, just an illustration of a kind of divergence you might face. So this isn't two sequences, this is one sequence. Okay, as you can see, this is how I go this way and then down. This is my order. So it is one sequence, not two sequences. So what can you say about its limit? What? The limit does not exist. How do you justify it?
Because it's divergent on a plane.
Well, yeah, but can you invoke the definition? So you can see the bands that I tried to. There is some kind of accumulation. Whenever you say that about limit says it's an accumulation, convergence towards something, it does. Look at it. It seems that accumulates here and there. Right. The definition asks for one band, and two bands won't do it. Okay, so that's you try to do it, and you can see the two it accumulates towards two values. Fine, and but in reality it actually oscillates between the two values. So which means that there is really no accumulation. Look at it. If you connect think about it in a more dynamical way. So. Which is actually a very, very productive way of looking at sequences. Forget about the n-axis or x-axis, and think about it as if you're progressing in time. That's what the sequence is. You can just think about every second you have a new location for a point, and you're just going up, and then what's happening here? It's just doing this. Is there a convergence? No, it doesn't have to. Think about it. How do you think about it? Looking at this picture the way I see it here, looking at this picture like that, it is almost the horizontal axis almost disappears, but I can see the pattern of what's happening with the 2 points. They go up and down, up and down. That's all I can see. So if you think about what's happening in time, this what will be happening, just like this. Up, down, think about it. So it repeats itself, but there is no accumulation to speak of. It will be oscillating. So if you see a process that actually goes back and forth without diminishing the swing, you know that there is no convergence. So what I'm talking about is, and it is kind of important, is here it is. Here's the illustration that might be helpful. As you can see, we're taking advantage of sequences. The simplicity of sequences is that we can actually think about them as a sequence of events in time, and then you don't really have to necessarily plot the time and just look at the events themselves. Just mark them appropriately. So this is the process that's happening. So we're moving from x1 to x2 to x3 to x4. And these are the numbers that are just moments of time, are 1, 2, 3, after 1 second, after 2 seconds, after 3 seconds. This is how we're progressing. And then if we wait long enough, we can see that those steps start to diminish, and then we start to see accumulation. And after that, the steps become invisible. And at that point, I'll take that red pen and put a dot here and say, well, that appears to be the limit. That's where we're going. It might be misleading because it's entirely, you cannot wait infinitely long to confirm that it's not going anywhere. But at least it's evidence. At least when you can distinguish this from the previous example, when you would have this. Left, right, left, right, left, right, left, right. Okay? So examples, a little bit more examples of specifically sequences and their limits. They are quite interesting. So 1n goes to 0, 1n squared goes to 0, 1n cubed goes to 0. The one we just did, negative 1 to the n over n, also goes to 0. And if you divide it by any kind of power that is high enough, it still goes to 0 as n goes to infinity. Sine n over n goes to 0 as well. So as you can see, some analysis that you did in Calculus 1 will apply. For example, for the last one, sine lies between negative 1 and 1, and you divide by a number that grows larger and larger, you know that it will be taken to 0. And what we did last time, just to confirm that this is the analysis, the squeeze theorem applies. So there is a squeeze theorem analog for sequences, which is what I roughly did here. So then there is a bunch of divergent sequences. So negative 1 to the n diverges. What else? Sine n diverges, and so on. You can think 2 to the n diverges. Many examples that just knowing how these functions operate will tell you convergence and divergence. Once again, something that really come as a bonus from sequences, even though it's simpler than functions, is how we deal with how about decimals. So 0.9, 0.99, 0.999, 0.99999. It is a sequence, and it converges to 1. Okay, so that is a question that they informally asked from mathematics students, is what is the difference between 0.999, infinitely many nines, versus 1? Is it the same? Is 0.999 equal to 1 or not? Is it? No? But what is 0.999 with infinity nines, many nines? That's really a question that you need to answer before you answer the question if they are equal to each other. What is the meaning of 0.99 with infinitely many nines? No, there's no n. Infinitely many nines, repeated infinitely many times. How do I understand it?
As a 1?
Well, that would be, but where did all the nines go? No, the answer is here. What is 0.99? How do I understand it? And the answer is, it is the limit of that sequence over here. Okay, so that is before you get to 1, you do this. You realize that there is no other way to understand infinitely many nines other than a sequence of limits with finitely many nines. So you know what 0.9 is. There is no doubt about it. You also know that 0.99 is. So all the numbers in the sequence are questionable, and they are, by the way, all less than 1. Okay. And then what is the meaning of infinitely many nines? And the answer should be, well, we just take the limit, if the limit exists, obviously, and that limit will be the meaning of 0.999. Okay? Once that is established, then we explain actually what we're talking about rather than trying to guess some answer that would be some satisfactory. Instead, what we're doing here, we are thinking of a way to treat all questions of this kind. For example, you can have the same question asked about 0.333. What is the meaning of 0.333? And the answer is, it is the limit of 0.3, 0.33, 0.333, and so on. So you create the sequence of finite decimals with which goes into infinity, and then you ask yourself what the limit is, and then you say that that limit, if it exists, is your number. That is the meaning of that infinite decimal. All infinite decimals might be explained, should be probably explained that way, as simply the sequence of the truncated decimals. So you have infinitely many, you cut it, you cut less and less and less, you make it longer and longer and longer, you have a sequence of real numbers. You can argue that the limit will exist. I'm not sure if you remember from Calculus 1, but what is so special about both of these sequences, what's so special about these two sequences? Well, I mean, yeah, you didn't have sequences in Calculus 1. So they are both increasing, and they're bounded. So all of these are less than 1. All of these are less than, say, 1 as well. Okay, so in other words, every time we do this, truncating the decimal, every time we end up with a sequence that is increasing and is bounded. And then there's a theory that says that, well, let me just state that. Every sequence theorem, every increasing and bounded sequence converges. So in other words, there is a limit. If there is a limit, then it makes sense to talk about it, and it is a number, not something else. It is purely a number, so we can just, wherever we say sequence, and it is convergent, we can assign a number to that sequence, the limit. The limit is assigned to that number because that's where that sequence is going. And once again, you can answer every question about infinite decimals in that manner, including rationals like these, 0.99 versus 1, 0.33 versus 1/3, right? It is 1/3 after all, or pi, or any kind of number that might have non-repeated representations. Decimal representation still works in the exact same manner. Okay, so that's the bonus that sequences give us in comparison to functions. We cannot really use it for this kind of analysis with functions, but sequences are more flexible. Okay, and then there's a theory of limits of sequences versus the algebra of sequences. So just like with calculus. So early in calculus, you might remember the interaction between sequences, the algebra of sequences, such as adding, or rather, I'm sorry, functions. You can add two functions, and then you ask yourself what happens to the limits. What happens to the limits? Two functions, they have limits. Add the two functions together, what happens to the limit? What about the limit of the result, of the sum? You also add the limits, okay? Same with subtraction, same with multiplication, same with division as long as the limit is not equal to 0. All of these rules apply. So let me state these. So it's called, the algebra of limits. And it totally follows the algebra of limits for functions. And it's more than once. Remember that the algebra of limits for functions goes on to the algebra of limits for derivatives. And the algebra of because the derivative is a limit. And then the same for integrals. So that's all pretty much the same thing. Okay, so for example, the sum rule. So if the limit of an is equal to a and goes to infinity, the limit of bn is equal to b and goes to infinity, then the limit of an plus bn is equal to a plus b and goes to infinity. Okay, so what's the difference from what you saw in calculus 1? Not a lot. Just we used to have here a function f of x. Okay, f of x goes to a like that, but the words definitely are the same, and that it needs to be taken care of. So this is the abbreviated version of the sum rule. The full version would state something like the sum of two convergent sequences is convergent. So that's the setup part, and then the punchline is the actual limit. And secondly, the limit of the sum is equal to the sum of the limits. Okay, so that is the full version of the sum rule in words rather than in formulas. So I'm not going to go into the details how you can use it to compute more limits. Just same as in calculus 1. If you have a limit, you have a sequence and you need its limit, break it into two if possible, and then evaluate limits separately. And if they exist, then you're fine. Then you know how to finish it. Then you have the difference. Naturally, you can have subtraction here. You can have multiplication. You can have division. Same story. Let me state at least one of them. So say quotient rule. So if we want to be careful, so the quotient of two convergent sequences is convergent when the limit of the denominator is not 0. Okay, when that's the case, then you say the magic words, the formula, in words, the limit of the quotient is the quotient of the limits. Okay, so, well, the formula is, abbreviated formula would be this way, an over bn, with all the caveats. The statement itself, what it's about the caveats to make sure that you don't jump to conclusions. But if you are justified, then you can, and then this is the conclusion that you might jump to. Okay, so the limit of the ratio is equal to the ratio of the limits. Okay. Okay, so those four rules. There is the fifth rule that is more challenging, but actually equally important. What's the fifth rule? There are four algebraic operations, but there is one more rule nonetheless. Addition, subtraction, multiplication, division.
Would there be a power rule?
Close, but not, there is a more general way of looking at it. What can you do with functions in addition to the 4 algebraic operations? Composition, right. So you can compose, including, for example, if you compose it with a power function, then you have the power rule. Okay, so the power rule, let me just, since we're talking about this, let's an power of m, limit n goes to infinity. Okay, so it is, whenever you see a lot of parentheses, well, let me put the more parentheses here to be clear, so that the whole thing is inside of the limit. So when you see a lot of parentheses, you know that you're talking about a composition, and in this particular case, as you can see, the sequence is an is followed by nth power. Okay, so that is the composition, consecutive computations, and then turns out that just like these rules, it can be broken into pieces as follows. You take the limit of an, and you take it to the nth power. So power rule. But I would really encourage you to think about this as a rule of compositions rather than just a particular power function. And well, then the question becomes, what is so special about the power function? So I'm talking about, say, y equal x to m. What is so special about this function that makes the rule work? If you remember from Calculus 1. Well, let me do another composition. So the power rule and then variations. How about limit n goes to infinity sine of an is equal to sine limit an goes to infinity. Okay, so once again, notice what has happened is there is their limit and there is that function. In the first case, it is the power function. In the second, it's sine. Okay, and what has happened is, okay, I'm sorry, I messed up over here. I flipped the order of things. Instead of what I have on the left, I first do the composition and then I do the limit. On the right, I first do the limit, then the composition, the other function. Okay, so as you can see, sine is taken out of consideration. So the sine is unconcerned as far as the limit of sine is not an issue anymore. Okay, so well, certainly that tells you something about the sine function, something nice about it. So what is so nice about it?
It's continuous.
It is continuous, right? So this rule applies to all continuous functions. Well, let me give you one more to complete the picture, hopefully. So limit e to an goes to infinity is equal to e to limit an goes to infinity. Okay? So y equal sine x, y equal e to the x. All of these are continuous. So as long as the function is continuous, you can flip these two operations, or probably a better way to think of it as it is taking the function, the exponential function, the last line, the exponential function is taken outside of the limit, right? It was inside the limit, now it's outside the limit. So you take care of the limit first, and then you deal with exponential function. So certainly that's why this rule also qualifies as a rule of limits, because it simplifies things. It simplifies things so that you can deal with one thing at a time. And so the general rule is, I'm not sure if there is a name for it. Well, in fact, it's not as much a rule as it is almost, unless it's exactly what it is. It is the definition of continuity. It is what characterizes continuous function. It is that you can do that with them. Okay, so if y equal f of x is continuous, at x equals, say, a, and limit an is equal to a, n goes to infinity, then, so two things to be verified, continuity and the convergence of the sequence itself. So that the right-hand side would make sense. We want to make sure that it makes sense ahead of time. So something like that, unless if an diverges, then we can, there is no formula. Okay, so the formula, which is limit f of an, n goes to infinity, is f of limit, well, let's just put a there, a. Okay, so you might, if you look at the last formula, this should resemble the definition of continuity, right? So continuous function is, well, this is what we're talking about. We're talking about the x-axis here. We have a here. The function is here. This is f of a, right? And then what are we talking about? We are investigating our behavior at a, okay? And x, a, y, okay? And then how do we investigate it? We'll look at sequences of a's like this, converging to a, and then what do we want to make sure of? We make sure that, let me put it here, we want to make sure that if we take it, the value of that function on the y-axis, there is a convergence there too. So we have convergence here, and converges to a, and we want to ensure that f of an also converges. That characterizes, that's what makes a function continuous. If it guarantees that there is no jump at a equal a, there is no jump of values like this. That would make sure that there is no convergence. So that is a very important property, and primarily because of its connection to continuity, and it shows that sequences are a tool for more than just one thing. So we'll talk a little bit more about this next time. Okay, the homework is due tomorrow. Okay.